Welcome to a quick discussion on escape velocity and the solving of example number 14. To help illustrate the concept of escape velocity, I'm going to use this simulation called My Solar System from the PhET website. It's downloadable, free. This object here, we'll say, is the Earth, and this little sphere here, let's say, is a rocket being fired away. And the red arrow represents the kinetic energy, which I can change around. I can give it different velocities. And what I'm trying to find out is what speed do I have to give this rocket so that when I press start here and let go of it, it won't slam back into the Earth. So obviously that was too slow. If I give it a bit more speed here, something like, I don't know, like this, fire it away and it's moving away, but still yet not quite enough speed because it's slamming right back into it. So I need to increase that velocity, maybe a little bit more, and let's press start. And you can see that it is indeed slowing down, but eventually will come to rest at infinite distance away. At that point, all of the kinetic energy has overcome the negative potential energy. So the key in solving an escape velocity problem is conservation of energy. The energy that the rocket has initially must be equal to the energy that it has finally. At the beginning, it has both kinetic energy and gravitational potential energy. And at the end, you could say it has gravitational energy and kinetic energy, as shown over here. The kinetic energy is given up by 1/2 mv squared, and the gravitational energy is given by gmm over r. In this particular case, since we're firing it right at the surface of the Earth, r would represent the radius of the planet, if you're trying to find the escape velocity from the surface of the planet. Big M and small m, big M would represent the mass of the planet, and little m would represent the mass of the satellite, or the rocket. Now, if you look at the kinetic energy finally, I didn't write the equations in here, but it would be 1/2 mv final squared, and the gravitational energy would be negative gmm all over r final. Now, if you are technically looking for the point where it would never, ever come back, that would be the essentially r reaching infinity. And if r approaches infinity, then this whole term will go to 0. And that's going to occur when all of that kinetic energy has overcome the negative gravitational energy. So when that occurs, there's no more gravitational pull acting on it anymore, and the rocket essentially has, at that particular point, stopped moving. You notice in the animation earlier that I showed you, it kept slowing down. So when you reach that limiting point, the final velocity is basically going to be 0. So this term is going to be 0. So in reality, the total energy at the end is 0. All of that positive kinetic energy is equal to all of that negative gravitational potential energy. So solving here, we'll see that the mass of the satellite is relevant. Cancels out. And this velocity that you get is really equal to the escape velocity, and it's equal to square root 2gm over r. Okay, so now let's apply that to example number 14. So if we were to find the minimum escape velocity to escape the surface of the Earth, what you need to know would be just simply 2 times g times m divided by r. In this case, m would be the mass of the planet, which is 5.98 times 10 to the power 24. That's what you would need to look up. You would also need to know the radius of the planet. I'm assuming you're firing the rocket from the surface of the Earth. That's 6.38 times 10 to the power 6. And so then you just need to substitute that in. And there we have all the substitutions. Notice I have to have the mass in kilograms and the distance in, not meters per second, but meters. And then we get an escape velocity of 1,118.1.96 meters per second. Let's just round that off to 11.1 kilometers per second. So that's how fast you need to fire a satellite at, a rocket at, from the surface of the Earth so that it does indeed escape the Earth's gravitational pull on it. Of course, if it escapes the Earth, it's not necessarily going to escape the sun. So, because you also know that it's going to be pulled, the Earth is being pulled towards the sun as well. So there are all sorts of escape velocities. You have the escape velocity for the moon, for Mars, sun, and so forth. And I just pulled this off quickly from the internet. It's a table of escape velocities, and you can see here the Earth is 11.2. I'm off a little bit here. Actually, I realized I should have been rounding that off to, it's not, yeah, it's 11.2. I'm not sure where my rounding off. Maybe there's a bit of rounding in this figure here and here. Anyhow, the escape velocity of the from the Earth is 11.2. Um, but you can see other planets that are close, like Venus is 10.3. The sun, if you happen to be on the surface of the sun, that's going to be a very, very, very large velocity to escape from the sun. Of course, as you get further and further, as r increases away from the body you're trying to escape, then your escape velocity becomes less and less. And of course, the larger the mass, the escape velocity gets much, much bigger. And if you think of, extend this to say black holes, if a black hole has an infinite amount of mass at a very, very tall, small radius, then the escape velocity for a black hole is infinitely large. Okay, that's it for this example on escape velocity.